Green's function and the radiation integral. To demystify this deep topic a little bit, I'd like to review a concept from linear systems. If we have a circuit, a component, anything electrical that takes in a signal that's linear and time invariant, one of the standard ways we model that system is by putting in a delta function. So we put in a delta function. Now we can't do that because a delta function is impossible to realize, but mathematically we can do it. We put in a delta function, and what comes out we call the impulse response h of t. So then, if we have an input that's different than a delta function, whatever input is coming into the system when we use it in practice, we'll call that x of t. We can then find the output of the system in a special way. We do that by convolving the impulse response with the input, and we do that as h of t minus tau x of tau d tau, and we work that integral, and we get from that the output of the system. Well, we're going to do the same thing, but for space. Space will be our LTI system. So how does that work? Well, the LTI system is defined by some differential equation, just as properties of space electromagnetically are governed by a differential equation. So for space, what we have is del squared plus k squared times the magnetic vector potential is equal to minus mu times whatever current density is radiating a signal. That J will represent an antenna. And our goal is to find A, from which we can find the electric and magnetic fields. So there's the differential equation. And what we need to find is we need to find the solution to that equation when the right-hand side is a delta function. Now, this is a little bit different. It's not a delta function in time, it's a delta function in space. In fact, that delta function is going to be delta of x times delta of y times delta of z. And that delta function is going to live at the origin. And what we're trying to find is we're trying to find the solution A to that delta function, and that will be kind of like the impulse response of space. And because that's the special solution, we're going to use the symbol G, and we call it a Green's function. So the big picture message of this slide is that the impulse response of space is something we call a Green's function, and that's named after the mathematician George Green, who first worked out a lot of these ideas. Okay, so now let's do something with this. First of all, what is the Green's function? It turns out that the Green's function for space, the scalar Green's function, is g, and we're going to need some complicated variables here. I'll explain these in a minute. G of r prime is equal to e to the minus jk, and then the distance between r and r prime, which we'll represent with the vertical bars, and then 4 pi times r minus r prime. Now, in the lecture notes, as well as in the book, sometimes we use the notation r, and that is a point in space represented as a vector. Now, that is exactly the same thing as little r. There's just different notations. Some places we use one, some places we use the other, but they're the same thing. So r represents a point in space. But things have gotten a bit more complicated in the radiation material. We have 2 points. R prime is where the source is, so we call that the source point. That's where our current is located. The point R is the field point, also sometimes called the observation point. Okay? So the R and the R prime are exactly like the T and the tau in the convolution integral. In the convolution integral, we had a tau, which represents the argument of the input. Then we had t, which represents the time variable on the output. The tau we're going to integrate, it goes away, and we're left with a function of time y of t. Well, the r and the r prime are going to play the same role in space. In fact, here is the magnetic vector potential, and in the argument I can use a big R or lowercase r, doesn't really matter. This represents the field point. That's where we're finding the magnetic vector potential A. Well, A is equal to mu times the integral of the Green's function, e to the minus j k r minus r prime over 4 pi, and then the same thing. And then j of r, oops, I accidentally switched from the lowercase r to the uppercase r, but don't be confused by that. It represents a point. And then I integrate over dr prime. Now this is a bit complicated. That actually stands for dx prime, dy prime, dz prime. What we're doing is we're integrating, there's a prime here, we're integrating over all possible values for the source point. Okay? Now things just got complicated here. I totally understand that. But I want to highlight that this actually is a convolution integral. In fact, I can write it symbolically as scalar Green's function convolved with the current source. And by convolution, I mean this type of an integral. So in linear systems, we have a t minus tau and a tau. In the radiation integral, we have an r minus r prime and then a dr prime. It's a three-dimensional version of finding the impulse response in the output of an LTI system. We're doing it in space instead of in time. So that's the way we typically understand this expression. Now our goal isn't really to get the magnetic vector potential. What we want is the electric field. So our process for modeling an antenna is we take the antenna, we represent the antenna as a current source J, which we put into Maxwell's equations. And from that we find A, using this integral that we just came up with. And then from A, we can find the magnetic field or the electric field. So our goal is really to get the electric field. The A is just a helper quantity, an auxiliary quantity. Well, if we go back to the earlier math and put some things together, it turns out that the electric field is E is equal to minus j omega mu. And then I have a 1 plus 1 over k squared. K is wave number. Then I have a gradient of a divergence. The dot means divergence. Then here I have the integral. And I'm going to write it in a little bit different way. I'm going to write g of r prime and j of r prime dr prime. So that g is the Green's function I defined at the top of the page. And I'll put this in a box. That is, oops. Let's see. That is our radiation integral for the electric field. And that's going to be our primary tool for working with antennas. So we take the current source, we work a convolution integral, that gives us A, then we apply some derivatives, that converts A to E, and then we have the electric field. And all the practical things we do with antennas stem from the electric field. From the electric field, we can get the radiation resistance, which is really important. We can get the radiation pattern from Wednesday's quiz. We can get the gain of the antenna, which is a really important figure of merit that dictates how directional the antenna is, main beam widths, and so on and so forth. So everything comes from the electric field. So the final step is to go from the electric field to what we call antenna parameters. So there's our process. Antenna, model is as a current. We get the magnetic vector potential, but that's kind of buried in a formula for the electric field, which is what we really want. And in the end, we get the properties of the antenna.